Hi Santosh, can you hear me and can you see the screen? Santosh, could you please respond? Santosh, could you please respond? Can you hear me? All right, no point of talking. Let me check. Yeah, my sound is okay. Deepak, can you hear me? Can you please confirm? And can you see my screen?
Yes, sir. I can hear.
Okay. And can you see my screen?
Yes, sir.
Okay. We'll start. This week is about AC circuits, single phase AC circuits. To some extent, AC circuits, I think all of you have studied already in your 12th level um, physics. Why I am saying single phase? Because later on in this course, we will also study three phase AC circuits, which are meant for high power applications. Oh, it looks like Santosh joined quite. Okay. Anyway, uh, my name is Shatush Shide. I'm a PhD scholar at IIT Bombay, Department of Electrical Engineering. I'm working on machine design for my PhD, and I am one of the course tiers of this NPTEL course, Fundamentals of Electrical Engineering, that is taken by Professor Devapriya Das from IIT KGP. And we take three doubt clearing classes every week. Mine is every Monday, 7 to not 7 to 6 to 8 p.m. 2 hour session. So our objective here is mostly to clear your doubts that you have while solving the problems or while watching the lecture videos, and to solve some sample questions that might appear, not exactly, but similar questions that might appear in the quiz and in the final exam of the course. Just wait a second. Yeah. So this is, as I said, is the week. This week is about for AC circuits. Uh, can you guys go to tell me if you have any doubt in AC circuits, any question, any doubt, or maybe lectures from the previous weeks also? I'll answer your doubts first, then we'll go for the problem solving. Any doubt? Okay. Today's class we will start with a general concept of power in AC circuit. Is a very important concept. I would request you to take a note and understand how this thing works. Later on, this you will encounter this uh, concept many times. Power transfer. So since we are now talking about AC, our circuits will have frequencies also. Right now, say I have an AC source. Okay, I have an AC source, AC voltage source, which is giving you a voltage of say V sine omega 1t. So the frequency of this source is omega 1, and it is supplying a load. It is supplying a load, some unknown load we don't know about, some load it is supplying, and some hypothetical load, let us say, which is drawing a current A sine omega 2t from the load. This much current it is drawing from the source, some hypothetical load. So you notice that I have kept omega 1 and omega 2 different. So I am trying to make this situation as generic as possible. Actually, what happens is in reality, the load in most of the case draws along in the fundamental some other harmonics. But let us just keep it like this, that some frequency voltage source is there and the load is drawing current at some other frequency. So what is the power that is being delivered to this source? Sorry, to this load by the source. So the instantaneous power is simply the multiplication of the instantaneous values of current and voltage. So Va sine omega 1 t times sine omega 2 t. Okay. Have I turned on the recording? Yes. So this is, I don't know. Santosh, are you here? I don't know. So this is the instantaneous power. So you can understand that if you multiply this, some power you will get, that will be like the instantaneous power. There will be some non-zero instantaneous power. Now we will try to find out the average power that is being delivered to this load by the source. So the average power will be Va sine omega 1 t times sine omega 2 t dt. So this becomes energy. So to make it power, we will do like this. So let us say this is the average power that is being delivered to the load. Now, if you do this, can you quickly tell me what is the formula for 2 sin A sin B? 2 sin A sin B is addition of that. No, that minus it. So it is cos, let me, cos of omega 2 minus omega 1 B minus cos of omega 1 omega 2 plus omega 1 t. Tell me if I am wrong. Right? So two sinusoids. The instantaneous power has two sinusoid components. One is this omega 2 minus omega 1, another one is this omega 2 plus omega 1. Now you understand that, say for example, let us take, say for example, if omega 1 is say 50 hertz and omega 2 is 100 hertz, then when you multiply these two, what you are getting, is 1 is 100 minus 50, there is 50, and what you are getting is 150, right? Now when we are doing the integration, we are trying to find out the average power. We have to do the integration over a complete period of the resultant waveform. So the resultant waveform, you can see, has 50 hertz and 150 hertz component. So we have to take the time period corresponding to 150 hertz component. Why so? No, sorry, not 150 hertz. The time period corresponding to the 50 hertz component. Why so? Because we have to make sure that the whole period repeats itself. So if this is the time period corresponding to 50 hertz component, in this time, the 150 hertz component completes 3 oscillations, right? So again, if I draw another cycle, you can see that the overall thing is repeating itself after only the period of 50 hertz cycle. So this t, we have to take, this t is nothing but the time period of this omega 2 minus omega 1, the lower one, right? Is it clear? So my point is, the overall time of integration that includes all the frequency components, then only we can call it an average. Once it uh, covers all the frequency components, then in this period 0 to t, both the components, cos omega 2 minus omega 1 and omega 2 plus omega 1, both the components, they complete integral number of periods. And what do you get if you integrate a sinusoid over a complete period? Integration over a sinusoid over a complete period, what do you get? Deepak, what do you get? Deepak, am I audible? It's like transmitting to the blind. No answer from the other side. Deepak, am I audible? Deepak, can you just say hi? See, your attendance is not counted for these sessions. I don't know what you do. Anyway, so average over a sine is 0. So basically out of this, what we are getting is this one also 0 and this one is also 0. So what we are getting out of it is 0. So the bottom line of this whole derivation is that unequal frequency or frequencies of voltage, we can say it in several ways. We can say we can say unequal frequencies of voltage and current, or we can say unequal frequencies of voltage sources, whatever, cannot transmit non-zero average power, right? So for average power transfer, non-zero average power transfer, there has to be same frequency component. So why I said average, because if you look at the waveform, say for example the waveform that I drew here, red and green waveforms, if I add them, you will get something like this. Maybe, I don't know, some non-zero instantaneous power you'll definitely get, but if you um, integrate that over a complete period, if you find the average, you will get zero power. So unequal frequencies of voltage sources, they cannot supply, they cannot transmit any power. Say for example, if you have an AC source of say 10 sine omega t and the load is say somehow it is drawing by for some reason some DC current of 1 ampere, then 2 sine omega t plus say 1 by 3 sine 3 omega t plus 1 by 5 sine 5 omega t, something this kind of current, say this source is this load is drawing, but the power that will be delivered to this load will only be due to this component of the current, because the frequency matches, and what about the other frequency components? They will also transfer power, but that will be non-zero instantaneous power. But if you find out the um, overall average power, the average power due to other components will be zero. Power will be only due to this 10 sine omega t voltage and 2 sine omega t current. Okay, is that clear? Okay. So the current waveform shown above of figure 1 is passed through a 20 ohm resistor. Find out the average power dissipated in the resistor. No point of asking, I will simply tell. So it's a periodic waveform, and if you start observing from here, see, you can start from any other point of your choice. You will see from here to here, yeah, from here to here, it's one period, right? The waveform repeats itself like this. You can say from any other point also. You can say from here to here also. Yeah. So how much is the time period of this waveform? The time period is minus 1.4 to 2.6, that is 4 second. 4 second is the time period of this signal. Now the question is find out the average power in watt dissipated by the resistor. Okay, so what we have to do is see, only during this zone, only during this zone and during this, there is power dissipation, or there is yeah, there is power dissipation in the resistor. So how much power is dissipated here? So what we have to do is we have to find the average power. So let us find out the total energy and divide the energy by the time, 4 second time period. So during, say, I will call this say zone 1 and I will call this zone 2. So during zone 1, how much energy E1 is dissipated? It's I squared RT. I is 4 ampere, so 4 squared times R is 20 times it's minus 0.4 to 0.62, so it's how much? 1 second. 1, so 320 watt, sorry, not watt, 320 joule is dissipated in zone 1 during this time, and during the other time the energy dissipated is 2 squared times 20 times 1, that is 80 joule. So the total energy dissipated in one complete time period is 400 joule. So the average power is the total energy, sorry, total energy dissipation by the second or the time period, which is 100 watts. So the resistance is dissipating 100 watt of power. But 100 is not in the option. Am I doing something wrong? Oh, sorry, it's 0.6 to 2.6. It is 2 seconds. 0.6 to 2.62 seconds. So 160. So 320 plus 160 give us 480. 480 by 4 gives us 120. 120 watt. If there is any question, you stop and ask me. I won't wait. If you stop and ask me, I will answer. The average power delivered to an impedance 6 minus J8 by a current of this is, so 6 minus J8, this is what kind of load? This is a capacitive load. How do I know it is capacitive? Because there is a negative sign, so it's a capacitive load like this, 6 minus J8. So the resistance is 6 ohm and the capacitor is minus J8 ohm. So capacitor cannot be ohm, right? Capacitor is farad. So how can I write capacitor as ohm? Because in the question, frequency is mentioned, right? So at this frequency, this capacitor gives you an impedance of or reactance of 8 ohm. At other frequency, it will give you some other impedance. So that's how it works. The question is average power delivered by that impedance by a current of this. So the capacitor does not dissipate any power, right? Only the inductance, sorry, only the resistance, this dissipates the power. So to find out the average power, all we have to do is I squared R. And do not make a mistake here. This is IRMS. Many a times in GATE exam, they do this kind of trickery. They will give you current like this and simply ask you to find the power. So what many students would mistakenly do, like I did, they will simply do I square times R. But this one is the amplitude. This is not the RMS. RMS is 10. RMS is 10 by root 2. So it's RMS squared, 10 by root 2 squared. I squared R. So what we have is 100 times 6 by 2, which gives you 300 watt. Sorry, 300 watt. Okay. We go to the next question. The value of Z in figure 3, which is most appropriate to cause parallel resonance at 100 hertz. Need to find out. So value of Z, they say, here there is a thing. Z is a general symbol for impedance. It can be, means Z means it's R plus JX, plus minus JX, right? But as I can see in the options, they have written only like this. It's a wrong question, wrong terminology. Should be very careful while writing terminologies. So what we will do is we will start as taking this as on a reactance, that is either capacitor or inductor, no resistance. Okay. Now, and also I think with the given data, we cannot have two equations for using which we can solve two data, resistance and reactance. Anyway, and one more thing is definitely the Z is going to be a capacitor, because all we have is inductor here, and we have to create a resonance in the circuit. So there must be a capacitor here, which will create a negative Jx, say, that will cause resonance. So what is minus Jx? Minus Jx is 1 by J omega C, right? Jx is 1 by J omega C. Okay, so we have 1 by Jx in parallel. So what we can do is let us find out the equivalent resistance, equivalent impedance of this circuit. So equivalent impedance of this circuit will be Z equivalent, which is 6 plus 2 plus, it's 4 Henry. 4 Henry, how should we write? Should we take it there? Okay, let me write it as 2 J omega 4, or J4 omega, 2 times 2 plus J4 omega. This 4 Henry inductor, which is parallel to a minus Jx, or maybe we can write, since we have to find out C directly, 1 by J omega C. Right, now we have this, so we have to find out the equivalent resistance of the parallel. So it's AB by A plus B, so 2 plus J times 4 omega times 1 by J omega C AB by 2 plus J4 omega plus 1 by J omega C. What we have to do is we have to now simplify this so that there is no imaginary term in the denominator. We multiply it with 1 by J, with J omega C. That makes it simpler, 2 plus 4 j omega, j4 omega by j times 2 omega c minus omega squared plus, sorry, minus omega squared 4c plus 1. Now, after this, it is known to you that you have to take the real parts together, imaginary parts together, and then multiply uh, both numerator and denominator by the complement of the imaginary number that you are getting in the denominator. So I'm not going through all the algebra. You can do, I believe. So finally, what we have to get out of this is the imaginary part. So if I write, okay, let me write the Z equivalent. So Z equivalent will come out to be some real part, and an imaginary part. So that imaginary part is J times mm, J times 4 omega times 1 minus omega square 4 omega squared c minus 4 omega c divided by 1 minus omega square 4 omega squared c whole squared minus omega squared 4c squared. So this is the equivalent impedance of the circuit when there is a capacitor. Now we have been asked to find out the value of the capacitor when the circuit resonates. How much value of capacitor should I put so that the circuit resonates at 100 hertz? So what happens during resonance at a given frequency? The circuit basically behaves as a pure resistive circuit at that frequency, right? So pure resistive circuit means imaginary part of the impedance expression should be 0. So this imaginary part of Z equivalent we have to equate to 0. If you equate to 0, what you will get is 1 minus 4 omega squared c minus c equals 0. And if you solve this and put omega as 2 pi into 100 radian per second, what you will get is a capacitor value of 0.63 microfarad. So if you put this capacitor in the circuit, you will see the circuit to resonate at 100 hertz. Okay, we'll go to the next question. In the following circuit, IT under steady state is how much? IT under steady state. Okay, so the specialty of this question is it has a DC source and an AC source in series. Now we have R, L, and C in the circuit, which are linear elements. So we can apply superposition theorem in the circuit. So what we will do is we will consider the DC source only first, and then we will consider the AC source only. And both the cases we will find out the steady state current and add them, which will be the steady state current of the circuit. So we will draw two circuits, one where only the DC source is present and the RLC, and the AC circuit where this is present. Now if the steady state current through this is this much and through this is this much, then what we can say is the steady state current of the actual circuit given to us, the main circuit, is addition of these two. Addition of these two. Now, in the first circuit, the DC circuit, what is the steady state value of the current? What will be I1 T at steady state? It will be 0 because it has a capacitor in series. So basically the answer to this question does not depend on this DC voltage source. Okay, it can be 10 volt, it can be 100 volt, it can be 10 kV. The answer will be the same. Now, whatever steady state current we get in the other circuit, the second circuit will be our answer. Now it is easy to find out. We have to first find J. J is how much? J is 2 plus J times 2 omega minus 1 by omega times 1. So 1 by omega is the value of J. What is omega? Omega is 2. Sine 2t they have written here. So sine 2t. So omega is 2. So what we have is 4 minus half, that is 3.5. So 2 plus J 3.5. So this is the impedance of this circuit at the given frequency. Now the current is 10 sine 2t. What we can do is, okay, let us write it in vector form. Okay, just write this in vector from 2 plus J3 omega. So square root of actually right now we can tell the answer. It is going to be this. Definitely A and B cannot be the answer because it is not going to be a DC current. C also cannot be an answer because the current cannot be in phase with the voltage, because we see that the circuit is not resonating. Is it resonating? It is not. The circuit is not resonating. So the current cannot be in phase. So C also cannot be an answer. So definitely D will be the answer. Right now here as an MCQ problem, we can say definitely D is the answer if they have done it correctly. We will see. What is the equivalent resistance? Sorry, impedance. It's 4.03. I dearly hope that you guys can find out this. And if you cannot, ask me. 3.5 by 4, that no, if what 4 2. Okay, let me write for you. Angle 60.26 degree. This much. Now if I want to write the source voltage also as a vector. So we have written Z as a vector. I want to write source voltage also as a vector. It is customary to write vectors in RMS, but for this, since we have to again find out instantaneous, we will write as instantaneous. But if you are given a question where nothing is mentioned and there are vector voltage and currents, that is RMS, that is the convention. So we'll take, for this we need not to, because we have to again transfer it back to instantaneous. So what we do is we take vector this. So what is the current vector? Current vector is V by Z, which is 10 angle 0 by 4.03 angle 60.26 degree, which gives you 10 by 4.03 will give you 5.29. Let us not believe them. 10 by 4.03. Goodness, in the solution, they have assumed there is a DC current. Wow. Anyway, so it's good that we didn't believe in them. So 10 by 4.0 is 2.48. Angle minus 60.26 ampere. Let me just cross check once. There is a capacitor in series. Yes, definitely under steady state there cannot be any current, any DC current. It will be purely AC under steady state. So now if we have to write it in terms of sign, we can write that, or not in terms of sign, we should say in time domain. It is 2.48 sine omega t minus 60.26 degree. This much. This is the answer. Not only that, they have assumed, they have taken a DC current in the solution, but also they have calculated the current as IDC squared plus ISC squared, and have written it as an AC current. My goodness. Okay, again, I hope that you guys can draw phasors. A1, A2, A3 are three ideal ammeters. A1 reads 8 ampere, A3 reads 18 ampere, A2 should read out. Now, AC ammeter, moving iron ammeter, they cannot tell you the phase. All they can tell you is the RMS current, right? But it's AC current, so you cannot simply say that A1, which is 8 ampere, and A2, which is 18 ampere RMS, so their summation is 18 plus 8, 26 ampere. That you cannot tell because they might not be in phase. Now we have to draw the phasor diagram to understand the relation between these two currents. Now we can see that it's a parallel circuit. So if it's a parallel circuit, what we have to do?
A3, excuse me, sir.
Sorry, yeah, go ahead.
So A3 reads 18 amps, sir. It's not A2.
Okay, they said A3. Okay, sorry. So this is 18 amperes. So you have to find out this. So again, we cannot say that it's 10 ampere because we don't know the relation between 8 and 18. So for that, we have to do what we have to do is we have to draw the phasor diagram. It's a parallel circuit, so we have to take the voltage phasor as the reference because all the components are getting the same voltage across them. Now I will take the voltage as the reference. This is the voltage, this is voltage Vs. Vs is the reference. Now there are two currents A1 and A2. Where are they present? A1, it's a resistive load, so definitely A1 is parallel to Vs, is in phase with Vs, and A2, it's flowing through a capacitor, so it must be a leading current. So A2 must be here. Now their vector summation A3 is what we are getting here as 18 ampere. Thanks for pointing out. Now the relation between A1, A2, A3, you can understand by Pythagoras theorem. It's A1 squared plus A2 squared comes out to be A3 squared. Now we can say 8 squared plus A2 squared is 18 squared. What I get is 16.12. A2 comes out to be 16.12. So the ammeter will read 16.12 ampere. Yeah. So just tell me one thing. So from this observation, can we tell that ACL is not valid in AC circuit? Is it correct to say? Definitely it is not, because first of all, instantaneous, if you see, KCL is always valid. Secondly, we are applying KCL. Definitely we are applying KCL, but not, these are not scalars, these are vectors. KCL is valid like this. A1 vector plus A2 vector is A3 vector. Okay. We'll come to this question. In the given network, V1 is 50 angle 0, V2 is 50 angle minus 120, V3 is 50 angle 120. Is three-phase voltage source. The phasor current I is how much? This current is how much we have to find. So what we can do is we can apply superposition theorem. So we'll consider the voltage sources one by one. So we'll quickly draw three circuits where the three voltage sources are individually present, like this. Like this. And this. And in all the cases, we have to find out, what we'll find out is the current through this branch, and we'll add them up, right? Now, if you look at the first two circuits, it's very easy to find out the current. See, there is one thing wrong in this question. I discussed this thing in the very first class, that you draw a circuit, you show a voltage source, you give an expression for that voltage, V1 angle 50 angle 0, V2 50 angle minus 120, everything is fine. But until and unless you show the polarity of the voltage sources, it is not correct. It is incomplete. So they have given the circuit like this. If I take the polarities like this, no one can blame me. They did not mention anything. So now one can definitely blindly argue that it's the customer take like this, but that is wrong. Okay, that's wrong engineering. Anyway, so we will take the polarities like this. Yeah. So for the first two circuits, you see in the first circuit, the capacitor is short circuited. In the second circuit, the inductor is short circuited. So there will be no current through the capacitor and the inductor in the first and second circuits respectively. So we can simply find out. We have taken them like this. We have taken them like this. Okay. So say I call this I1, I call this I2, call this I3. So what I can say is minus I1 is 50 angle 0 by J1. J1 is 1 angle 90. Okay, I will draw it just below this. 1 angle 90, which gives me 50 angle 90 minus I1. Okay. Similarly, here also I will write minus I2. I think you can understand why I'm writing minus I2. It is again 50 angle, it's minus 120, I believe. Yeah, 50 angle minus 120 by minus J1. So 1 angle minus 90 minus J1 is 1 angle minus 90. Yes. So it comes out to be 50 angle minus 120 plus 90 minus 30. Okay, all are degree. All are degree. This and I3. I3 is there are two things in parallel now. There are two things in parallel. So it is 50 angle 120 by J angle 90 plus 50 angle 120 by J angle minus 90. I'm sorry, why I'm writing J angle? 1 angle minus 90. 1 angle minus 90. Okay. So that gives us 50 angle 30 plus 50 angle 210. Right. Now, what is I1? I1 is 50 angle minus 90. I2 is 50 angle 30. And I3 is I3. Okay. All right. Now, what does this minus 90 angle minus 90 or whatever? Let me write in a different ink. We'll deviate a little bit. What does this mean? See, whenever we solve this problem, first of all, you have to make sure that whenever you are writing these angles and all, you have to make sure that you are consistent with sine and cos. Okay, you are consistent with sine and cos. What I mean to say is, say if you have a voltage, two voltage sources in a circuit, say like this. If you have two voltage sources in a circuit, one of them, 5 sine omega t, other one is 5 cos omega t. Now if you take this as 5 angle 0, you have to take this as 5 angle 90. It is also possible to take the other one as 5 angle 0, then you have to take this as 5 angle minus 90. Okay, it's like this. So let us say since in this question we have not told anything about sine, we can take whatever we want. At the end we have to answer in vector only. So let us take theta as sine, means this one is sine theta plus j cos theta. Okay, sometime, not sometime, this can also be written as e to the power j theta. It's very interesting. Just take this as x, differentiate, then integrate. You will directly get e to the power j theta. Okay. Now this is it. So basically the 50 angle minus 90 that we have here is 50 sine minus 90 plus j cos 90. Oops, I'm so sorry. It's cos theta plus j sin theta. Like this. Okay, so you can take it like this. Now for all the components you do this, then you take all the real parts together, you take all the imaginary parts together, calculate the value, you get something real plus imaginary, and that will be the final answer. Now what I am doing is I am using a calculator. Now make sure that you practice like this. In GATE you won't be able to use calculators like this, but in exams and all, in university exams, you can use. I am using this one. This one I am using. This can directly do a vector calculation. So I will be using that feature of the calculator only to directly find out. So I am writing in my calculator 50 angle minus 90 plus 50 angle 30 plus again 50 angle 30 plus 50 angle. I'm simply adding up all these currents, angle 210. So what I'm getting is the total current I as 50 angle minus 30. Somehow I don't know why the answer is not matching. This is the current. Let me quickly check whether there is a mistake. I1 we found like this. Angles are correct. Angles are correct. This is 90. This is cap. So minus. And this is 50 angle. This is 120, right? 50 angle 120, yes, 50 angle 120, J1, so 1 angle 90, 1 angle minus 90, 50 angle 30, 50 angle 210, and then I reversed the values. Let me do it once again. 50 angle, sorry, 50 angle minus 90 plus 2 times 50 angle 30 plus 50 angle 210. Yeah, I'm getting 50 angle minus 30. So this is the answer. This is basically a simple application of superposition theorem and then vector addition. Vector addition, if you don't have a calculator to do, you can break them up in cos and sine and then calculate. What I can see in the solution, they have made a mistake. The third current they have not taken. Is it wrong to take the third current? No, it is not. It is not, because these are voltage sources. So voltage sources we replace by short circuit. Yeah. So this one is the correct answer. Not doing any mistake. No. Okay. Next question comes: a series RLC circuit is observed at two frequencies at omega 1 kiloradian per second. We note that the voltage source V1 is 75 angle 0. That results in a current of I1 2.12 angle minus 45 degree. At omega 2, it's half kiloradian per second. The source voltage is 75 angle 0. That results in a current 3 angle 0. The closest value of RLC. Okay. Before we do this problem, solve this problem, I want to discuss something. See here. Okay. Let us have a general discussion. Suppose there are two, the red color changed. Okay. Two sinusoids. Let me draw it other color. Two, not necessarily sinusoid, can be anything, but it should be periodic. Okay. Any periodic waveform like this. Now, we know that this is how we find out the phase difference between them. The blue one is lagging by certain phase difference in this fashion. But here I have drawn them in the at the same frequency, or I have to say waveforms the same frequency. But now if say I have two waveforms, both periodic, but they are not of the same frequency. Let me try to draw like this. Something like this. So the blue waveform has a frequency twice than that of the green waveform. So in such cases, can we define a phase difference? We cannot, because it keeps changing. So phase difference or whatever is valid only when you are comparing periodic waveforms of similar frequencies. Similarly, for the same reason, phasor diagrams, on a phasor diagram, all the phasors that you have, they must be of the same frequency. All of them must be rotating at the same speed. Then only you can draw all of them in the same phasor diagram. Now, why I'm telling you is this is, you see, this problem talks about two frequencies. One is here and other one is here, two frequencies. And for both the cases, they have written 75 angle 0, 75 angle 0, and this minus 40. So remember that the angles of the first case and the angles of the second case, they are corresponding to their frequency. They cannot be compared. Okay, just keep that in mind. Okay. So the question says that they did an experiment and at two frequencies and they got these results. I think the second result is more interesting. The second result at this frequency is more interesting because here the voltage and the resulting current, they are in phase. What does that mean? It's a RLC circuit, but still the voltage and the current are in phase. So definitely the circuit resonates. At this frequency. Circuit resonates mean what? So it's an RLC circuit, R, L, and C. Circuit resonance means at this frequency, if we have Jx from the inductor, we have minus Jx from the capacitor, so that the circuit is purely resistive. So if the circuit is purely resistive, from this information itself, we can say that the resistance present in the circuit is 75 by 3, that is 25 ohm. This resistance is independent of frequency. It doesn't matter how much frequency is there. Okay. So the second set of experiment gives us the value of the resistance. Now we have to find out the other thing. Now we don't have enough data. We have two more. Or do we have enough data? Let us see if we can find out. Actually, it's an MCQ question. So you can say that C and D are completely out of the picture. Now what we can do is you can simply find out the phase difference. I'm sorry, yeah, phase difference. So it's I1 angle minus 45 degrees. So at that frequency, definitely the circuit is inductive. Has to be, because at half radian per second it resonates. Now I am operating at a frequency higher than the resonant frequency, so inductor dominates. So at that frequency, if I have the resistance current like this, the inductive current is like this, and the capacitive current is like this. So if I subtract capacitive current, then if I do vector addition, this much this much current. So this is the resulting current that we are getting at minus 45 degree. The voltage is definitely in this direction, right? So this we have to find out how much is this. So if this is theta, then the whole thing, this current is V by J XL. No, I am doing a mistake here. See, I told you there is something that in the previous one, that it's a, that the previous question was not this one, parallel circuit. So we had to take voltage as the reference. Now this one is a series circuit. Series circuit means they all have the same current through them. So we have to take the current as a reference. This is the current flowing. Now we have to draw the voltages. So the voltage across the resistance is this. Voltage across the inductor that will lead the current, and it will be large. That will lead the current, it will be large, VL. And voltage across capacitor will lag the current, be like this. Now if we do vector addition, VC comes here and VR is in this direction. Wait, let me draw it clearly. VC, VR was in this direction. So the addition is this. This is the source voltage, VS, the total voltage, VS. Now this is theta. This theta we have to find out. So this one voltage is V time J time VXL, and this much is J time VXC. I am writing, okay, I am writing only the dimension, okay, not the vectors, only dimensions. VXL, this dimension is, this length is VXC. So what we have here is V times, sorry, not V, these are voltage, I, messing up a lot today, I. So the voltage, the dimension that we have here is I times XL plus, sorry, not plus, XL minus XL minus XC. And this is, and this much we know. So what we can write from this diagram is tan theta. Tan theta is height, that is XL minus XC by base R, this. Now they have said that 45 degree is the angle. So tan 45 degree is 1. So 1 is XL minus XC. This much we have from this equation, equation 1. And also we have the total current, right? So from the current, can we say something? So the Z equivalent is R plus J times XL minus XC. So if I write the modulus, that comes out to be R squared plus XL minus XC squared. So V by Z, if I write RMS, 75 by square root of value of R we know, 25 squared plus XL minus XC squared. This is this current 2.12. Now if you solve this, you will get the values of XL and XC. Now I was thinking that, so this is the way of doing it. Like if you are solving this problem in your semester exam, you have to solve it like this. You have to solve 1 and 2. But say if you have this question in a competitive exam and where you have the options, can we have an easier way of solving this? See, we know the resonance frequency of this circuit, right? So at resonance, what happens? At resonance, omega L becomes equal to 1 by omega C. So basically, what we have is omega squared is equal to 1 by L LC, right? Now it was resonating at how much? Half kiloradian per second. It was resonating half kiloradian per second. So 0.5 times 10 cube, half kilo. This should be equal to LC. So we have two options, 33, this and this. These two have already discarded. They cannot be the answer. So what you can do is from here, you can quickly verify. So 33.33 times 0.12, both are milli. So both are milli. So it becomes 10 to the power 6 here. So we have to just find out how much it is. 33.33 times 0.12. It gives us somewhere close to 4. This I think cannot be. Let us see the other one. 0.12 times. Hey, they're the same thing. Oh, okay, okay. So no, this is not going to give you the same answer. What you are getting is out of this 10 to the power 6 by 4, which is this one basically 0.5 times 10 cube. So they have done a trickery here. Just by looking at the resonance frequency, we cannot solve. We have to anyway solve these two equations. Is there any other way? I'm not going to solve these two equations. I believe you can solve this. This two equation you can solve. Oh, this is easy to solve. XL minus XC is 1. So it's 75 by square root of 25 squared plus. Are we getting something? Looks like we have to think more systematically here. Okay, let me just check. Am I missing something? Solving these two is not giving us. This is not 1, this is 25. How can we somehow eliminate? Okay, so basically these two equations, they are actually the same. You cannot solve from here. So 1 and 2, these are not the two equations. Other equation is this. You see, from here we cannot solve. Other equation is this. One equation comes from the current, other equation comes from the resonance. So omega squared is 1 by LC. They have given. From there you have to replace, say, find L in terms of C or something, and put it here. XL you replaced by j omega L, and XC replaced by 1 by j omega C. Do you need to write J? No, it's modulus. So X omega L and 1 by omega C. And this omega is at the other frequency 0.5 kiloradian per second. Okay, so that much you put, and L and C value you replace from here, you will get the values of XL and XC. I will just tell you the answer. Answer should be option A. Do it yourself and see if it matches. Any doubt how to solve? All you are left with is to solve the equations. Okay. Question is determine the average value of the current waveform. So average value we need not do for the whole thing because it's periodic. Yeah, we'll do until this, from 0 to this, right? So let us quickly find out the areas. This area and this area, say I'll call this area A1. If this is A1, this is also A1 because their height are same and base are same. And this one is A2. So A1 is half into base into height, which is T times IP by 4. Area A1 and area A2 is it's 3T by 2. So 0.5 T by 2. So for T by 2 it is IP. So TIP by 2. So the total area is 2A1 plus A2, which is TIP by 2 plus TIP by 2, TIP. And the time period is 2T. So average is TIP by 2T, which comes out to be IP by 2. No, sorry. It's average. So these are negative. A1 it was negative. So what we have is minus 2 times TIP by 4 plus TIP by 2, which gives us 0. This is a 0. I missed it. This is a 0. So these ones are, their areas have to be taken as negative. So what we have is 0. Okay. How many more questions? 2 more questions. So this is the question for which I had the discussion at the beginning. A voltage VT 15 plus 75 sine 276t plus pi by 6 is applied to a circuit as steady state current is given by it. This much. It is through flowing through the voltage source. Determine the average power. So we have two frequency components here. In the voltage, we have a DC and we have 75 sine whatever I will write omega t minus sine naught minus plus pi by 6. In the current, what we have is another DC component 15 plus 25 cos omega t minus pi by 4. So first thing first, this is sine, this is cos. Okay, we will make both of them sine or both of them cos maybe. So what we have is sine 90 degree plus theta is cos theta. So this we will write as IT plus IT 25 plus 25. So if we add 90 to this angle, this becomes sine omega t. It was minus 45 degree plus 90 makes it 45 degree. This. Now what I will do is I will copy this. Okay. So this is what we have, currents and voltages. Why did I converted both of them to sine, or we could have done both of them into cos? Because you have to find out the power. To find out the power, you have to find out the phase difference, right? Sine 90 plus theta is cos theta, so I added 90 to this, and this became pi by 4 just plus pi by 6. Yes. So as we discussed at the very beginning of this class, interaction between these two components and interaction between these two components will not give rise to any steady, any non-zero average power. There will definitely be power that will be pulsating. There will be non-zero instantaneous, but average, if you find out, the average will be zero because their frequencies are different. Only meaningful power or non-zero average power that we will get out of the interaction of these two voltage and current sources or current signals are due to interaction between these two and interaction between these two. Right? So there will be four components, out of which one is completely DC, three are AC, and out of those three AC components, two of them do not give any average power, one of them give average power. Right? Now, these are DC values. So DC power is 15 times 575 watt, and AC power is VRMS IRMS cos phi. So IRMS VRMS cos, just the difference. This is 45, this is 30, 15 degree. So whatever you get, that is the answer. Is it clear that we don't have to consider interaction between this and this? Do not, this thing I am telling you again and again, do not think that there is no power because of the interaction between them. There is power, there is pulsating power, and the average of that pulsating power is zero. There will be no power. Okay, we'll go to the next question, which happens to be our last question for today. The following circuit resonates at which frequency? Okay, so 4, we will write 4 as J4, 1 as minus J, 1 as minus J omega. So what is the impedance of this circuit? So only the right hand side, this part only gives the impedance. We have to simply make it 0. It is J4 omega minus J times 1 by omega parallel to minus J omega. This is nothing but a simplification problem, whether you can, sorry, AB by A plus B. Oh no, yeah. Simplification problem, it's simply whether you can do complex algebra, nothing else. So I will take all the J common. So if I take the J common, 2J come out, it becomes J squared minus 1. That minus 1 gets absorbed. So we have here 4 omega minus 1 by omega times omega by, again I will take the J out, and how much? A plus B. So 4 omega minus, this is J by omega. And 4 omega minus 1 by omega, sorry, plus minus 1 by omega. This is what we have. So we have to make this 0. Simply make the numerator as 0. If you make the numerator as 0, what you get? You get 4 omega as 1 by omega, which gives you omega squared is 1/4, and omega to be half radian per second. Just let us see one thing. If I put omega equals half in the denominator, what comes? Comes 2 minus half minus half. So it, oh sorry, half is I'm putting. So 2 minus 2 minus 2. So it's not 0. Fine. Not 0. Should not be 0, the denominator. So at this frequency, this circuit will resonate. Okay. So that's all for the problems today. Now you guys tell me if you have any doubt anywhere in this class or previous class. I will answer your doubts, or else we'll call it a day. If there is no doubt, you can leave. If you leave, I will understand that you don't have any doubt. Or you can stay for others' doubt also, if you want to listen. Or can you just tell me that you don't have a doubt? Deepak and Monica joined later. Okay, Monica left. Deepak, any doubt? Deepak, can you hear me? Deepak, can you just say hi? Okay. Let the recording be on.